So my inclination is to lead off with a fairly open-ended question and just let each person comment on what they think are the really interesting open questions in our field, this kind of emerging field at the intersection of quantum information and high-energy physics, and what are the promising approaches and what they envision for the future.
20 minutes each.
Well, I have other questions. We'll see how many we get through.
Okay, well, I guess maybe I'm a little bit of an outsider to this kind of, quantum computing meets high energy. But as I discussed in my talk this morning, I think a nice question is the extent to which quantum computers will really be kind of practical relevance to solving problems having to do with understanding quantum field theories. It seems like this is a situation where you have to consider a fairly large-scale system before you can sort of really be asking interesting questions. So hopefully at some point we will have really large-scale quantum computers and we can do that. But I think this is a nice question, sort of what we can hope to do with realistic devices.
I mean, Stephen, it would always be more tractable to ask us what are the closed questions in this area, right? I mean, there's so much, but I mean, one of the biggest things that I would love to see is just, investigation of, taking into account everything that we've learned about physics, sort of what can we say about, is the physical Church-Turing thesis true? Is the polynomial time Church-Turing thesis or the quantum Church-Turing thesis, let's say, true, right? What are the ultimate computational abilities, of our universe, right? So, I mean, in my talk, I talked about sort of a more speculative branch of that question, I guess. John, in his talk, talked about, well, what about just the quantum field theories that we actually know? Can we simulate them on a standard quantum computer? Obviously, there's a lot more to do there. One very basic question should quantum gravity at least be computable? Right, so Roger Penrose famously conjectures that quantum gravity should be the source of the uncomputability that he's certain must be present in nature. But ironically, quantum gravity may do the exact opposite. Right, it may be the thing that imposes computability, on laws of physics that would otherwise be uncomputable. Okay, so what does ADS-CFT have to say about that question? Sort of, can we give sort of a general argument? For nature being computable, assuming, based around ADS-CFT. That's something that I would love to see people thinking about.
Well, I don't know. For me, I guess, this question can be answered on various timescales. Say on the 5-year timescale, for me, the question which I would really like to understand is how to think about the interiors of black holes and quantum gravity, and in particular in ADS-CFT. So you probably heard there are these various famous paradoxes going under the general name of firewall about to what extent the interiors of black holes do or don't exist, to what extent they do or aren't described by quantum mechanics as we know it. I don't know. I would like to know very much. I guess partly just curiosity, right? It's it's an experiment we could imagine doing. And if someone comes to you on the street and they tell you that they have a theory of quantum gravity, you should ask them what's the answer to this question. And for a long time, we hydrogen physicists were saying, we have a theory of quantum gravity. It's this ADS-CFT correspondence, and then people pointed out that we didn't know the answer to this question. So I think it means we don't have a theory of quantum gravity. We have part of a theory of quantum gravity, and we really need to sort it out. On the longer time scale, I think that this will be very important for making sense of quantum gravity and cosmology, which is important because, as I said in the beginning of my talk, we don't live in anti-de Sitter space. There are many interesting parallels between the interiors of black holes and living in an inflating universe. And by the way, the paradoxes are even worse than the paradoxes about the interiors of black holes. But on the other hand, those ones might actually have some sort of observational consequences in the not too distant future, or maybe even already. So it's something that we, as scientists, really owe it to the community to understand. So it seems and for me, so for me, quantum information, quantum computing, it's a tool, right? I study it because I could use it to study these problems. And so I was totally on board with Andrew's talk. I don't know why people talk about like quantum supremacy or like factory. Who cares, right? Like it's just simulate QCD. That's already useful. That's what I want a quantum computer for. So and maybe the black hole interior too. Right? I don't know.
Well, I agree with everything that I think Danny was saying. And in particular, I think the problem of understanding the interior of a black hole is a problem where we are poised to make significant progress in the near future. And we want to flesh out, I think there are great opportunities in expanding on what we've learned about the connections between quantum entanglement and ADS-CFT and emergent geometry, making some of those ideas more precise. I used to say that the thing that physicists should know about that the quantum computationalists know is error correction, quantum error correction, but that's kind of out of date now because a lot of physicists know about that now. And in the case of condensed matter, it's become sort of commonplace that if you're trying to understand the renormalization group fixed points that represent quantum topological phases of matter, then you should think about quantum codes. And now thanks to Daniel and his collaborators, we're looking at ADS-CFT from the point of view of quantum error correction. And for 20 years we've relied on this crutch of ADS-CFT, but it's not the real thing, as I think someone said today. It's the toy model that's our warm-up for attacking questions like how to do quantum gravity in de Sitter space, where we actually live. And I'm hoping that some of these ideas about quantum error correction, as we get a better grasp on them, will help us extend our understanding of holography beyond just ADS-CFT. And as far as the quantum Church-Turing thesis, I think a step in that direction would be making more precise what we mean by ADS-CFT. It's a funny thing when we speak about a dictionary relating to theories, but we can really only define one side of the correspondence. We know what a CFT is, more or less, but the way we describe non-perturbative quantum gravity is by saying it's the thing which is dual to a CFT. And I think there will be in the mathematical physics books of the future a theorem which will say two things are equivalent where both of them will be defined, and like all good theorems, the hard part will be finding the right definitions of quantum gravity so that we can say exactly what we mean when we say it's equivalent to a boundary field theory.
I guess in my opinion, the intersection between these two fields simultaneously could stand with considering complexity classes that are both larger and smaller than the ones that are in existence now. I'll explain what I mean so it doesn't sound like I'm just spouting nonsense. What I mean is that if you consider what happened in Andrew's talk, some of the things that are known are, for example, in a 1+1 dimensional generic gapless field theory, it's been proven that finding the ground state of such theories is QMA complete. For people that are not quantum information people, that means that it's the quantum version of NP complete. Whereas if you give me a conformal field theory that has a holographic dual, finding the ground state energy of that takes constant time. I literally just look at the 0,0 component of the stress energy tensor and I have it immediately. So one thing that might be interesting is, in some sense, for the complexity theorists, with help and input from high energy physicists, to constrain the kinds of questions they're asking in computer science to problems that are more physically relevant. So for example, if you could, for example, tell me what the generic complexity of computing the ground state energy of a conformal field theory is, regardless of, without caring even at first if it has a holographic dual, that would be, for example, more interesting than some sort of generic gapless theory, many of which are not physically relevant. Another question which I would, what I mean by looking at complexity theory instances that are more powerful than the ones that we currently look at is, for example, the question of is BQP equal to something that I like to call BQGP? So what I mean by that is that if I modify the gate set that one has access to from one that's universal for quantum computation to gates that maybe one has access to if one factors in quantum gravity instead of simply quantum mechanics, does that enhance the power of quantum computation or not? The default answer in ADS-CFT, as I think a few other people have said, 10 years ago would have been no, BQP should equal BQGP. But because we don't yet have a concrete answer to, for example, the information paradox, we don't know this to definitively be the case. And because we don't know it definitively to be the case, it can be viewed as either a problem or an opportunity to better define another physical complexity class that maybe invalidates the Church-Turing thesis or causes it to be extended again.
Okay, I have a slightly different point of view about things. Not that I'm not interested in fundamental problems, on the contrary. For me, I think the basic questions like what is quantum mechanics versus general relativity, and is there anything new in quantum gravity, is the essence, and not necessarily can we build some machines which can do QCD, which is of course also very useful and very nice. Regarding the relation of quantum information to quantum gravity and quantum field theory, I think that somehow it sounds to me that the quantum information community sort of lives in a sort of a very abstract way of thinking about things rather than, or even in the ADS-CFT, essentially, actually what I hear is that things that might be very complex are translated to notions which are very simple in entanglement theory. That's fine, but there might be a missing thing. For example, if you think about entanglement in quantum field theory, it has a much more complex structure than we are familiar with in non-relativistic quantum mechanics. It has other things which are not there, and usually people ignore it. And for example, the notion of particle, of course, is not well defined, and there are stronger notions of entanglement because a particle is not local; it always carries a tail. There is the so-called Rich-Leader theorem, which is very surprising. It sort of shows you it's equivalent to the statement that entanglement is much stronger. It appears between many regions simultaneously in space. So these sorts of questions I feel are a bit kind of neglected. Might be completely irrelevant when studying ADS-CFT, but I'm not quite convinced that this is a picture of quantum gravity, because after all it deals with anti-de Sitter space-time where the trajectory is such that after a finite time an observer reaches to infinity, and so it's kind of a very special feature, and of course the results, the Utaka-Yanagi, is very, very intriguing and interesting, but I would leave a place for a bit of skepticism about it, because it could be that nature decides to do error correction, but it could be that it's also a misleading direction. So I would kind of advise or would like to see an approach which is kind of more open to fundamental problems which are not necessarily in the mainstream now, even just and in connection to this QCD simulations, etc. The thing that I find most interesting here, and John noted about it, is once you do it, once you build up a notion, a model for rotors, which and left and right a set of commutators, turns out that it gives you some intuition about the structure of entanglement on a link, for example, something that I personally never had. When I think about Young-Mills field theory in the continuum, it does not tell me anything about the structure of entanglement at a very short scale. So, and we know, for example, that when we think about spin form or other structures or loops, electrical loops, they are equivalent to in some sense, or they are connected in some sense to SU2 theories, gauge theories, at least in this context. So it might be related also to quantum gravity. And this is kind of a very different direction in some sense compared to ADS-CFT. So I would kind of be happy to keep everything, I mean, to leave it as an open question in general and not to, I mean, complexity is interesting, but it might be relevant to know, I don't know. So, okay.
Thanks. Yeah, so I guess what really excites me right now is how chaotic and in flux our understanding of what is easy and hard, both classically and quantumly. So, for example, on the classical side, it's long been the case that if you're interested in the equilibrium physics of systems with dynamical fermions, say, which is pretty much par for the course in condensed matter systems, also in QCD, that there's not much you can really say. You can't really do quantum Monte Carlo, you can't do exact diagonalization, you're running out of computational power, so we just don't know. You can ask to experiment, and that's interesting, but experiments are often very complicated, there are lots of moving parts, you can't necessarily get a clean answer out. However, recently, in the last, say, 15 years, by thinking very, very hard about entanglement, about the structure of entanglement in these kind of equilibrium quantum states, we've built a new set of methods, which usually called tensor network methods, which in one dimension have been enormously successful, and in higher dimensions, at least my feeling is that we're right on the edge of having a new kind of flood of results and breakthroughs that will let us really tackle problems we couldn't ever tackle before, and will really change what we think of as being easy and hard from a classical point of view, simulating the static or equilibrium properties of quantum many-body systems. And, I think one of the interesting questions actually in this direction, which is what I'll talk about on Wednesday, is if you can use small quantum devices to actually help you perform these classical simulations. So some sort of quantum-assisted classical simulation of many-body physics or quantum field theory. And I think it's actually plausible that you could do such a thing. Now on the other side, we're with these different kinds of analog quantum simulators we heard about, for example, these cold-atom systems. We are gaining the ability to design Hamiltonians, to design systems, and to conduct experiments where we're really probing physics that we have a good reason to believe is hard for a classical simulation. Okay. For example, if you can engineer a system with a certain Hamiltonian, maybe you can also engineer a system whose Hamiltonian is the minus of the original Hamiltonian. And then that would correspond to being able to rewind time in that system. So you can go forward and you can go backwards. Now from the point of view of a quantum circuit, okay, you're just changing some U's to some U daggers. Maybe it's not that dramatic. But from the point of view of physics, it's a completely different capability, and opens up the door to asking all new kinds of questions. And so I think we're sort of on the verge both of solving a lot of old, hard problems classically, but also getting access to new, hard problems quantum mechanically that will sort of require us to develop a whole new set of tools. And somehow the exciting thing to me is that at this very chaotic interface of these two sort of sides, easy and hard, a lot of cool ideas are intermixing. So you have ADS-CFT, you have black holes, you have quantum gravity, you have entanglement, quantum information, old problems in condensed matter physics. So it's a really exciting and I think very rich interface, and that's sort of what I think is going to be really interesting to see in the next, say, 5 years.
Thanks. So one of the things that's good about these meetings, one of the purposes of them, is so that the different fields that come together can learn from each other. The computer scientists can learn from the physicists, and the physicists can learn from the computer scientists. So one thing I'd like to pose to the panel is to the computer scientists, what's something that you know that you wish that the physicist knew, and to the physicist, vice versa? And in the context of this panel, I maybe don't need to say this, but if you want to, you can take this as an opportunity to make jokes at the expense of the other field.
What are you? Yeah, that's maybe you can pose that question to the panel. So I'm not sure that I understand the question actually. So something that I as a
Let's say you as a
computer scientist, okay.
That you'd like to make them aware of, that you think they should, would be a useful thing in their work in this field so that they don't get confused or go down the wrong track. You don't necessarily have to go first. We can come back.
Yeah, I'll pass.
All right. Well, let me. Since I think I'm the only one here whose degree is in computer science. Is that right? All right. So why don't you guys just sort of let me have it? I don't know.
I already know your answer to this question, right? Because because Lenny asked this at Stanford. I can give your answer.
Yeah, because I don't remember. So what
Right, so,
what was my answer?
so Lenny asked exactly the same question. Is there a
Okay.
notion in your field that physicists should learn about? And Scott said yes, the notion is proof.
I was just trying to piss him off.
Okay, I guess I'll also give the same answer I gave at Stanford, which is that time translation is a gauge symmetry. I already said it in my talk today, but it's important, so I'll say it again. In the bulk, there's no such thing as time translation. The Hamiltonian is 0. So that's a general property of diffeomorphism and variant theories, including quantum gravity. In conversations that I have with information theorists, time and time again, this is the source of confusion, because there's a sense in which the time evolution is the usual time evolution that we know on the boundary, but in the bulk it's not. In the bulk, the time slice can be moved up and down. It doesn't matter. The boundary, where it's attached to the boundary matters, but in the bulk it doesn't matter. And I think this is probably going to be important for understanding the black hole interior, because it's sort of it's what makes the time. It's what makes the evolution of the bulk mysterious from the boundary point of view, I think.
Is this just the usual issue of the difficulty of defining time in quantum gravity?
Well, I'm not sure I'm not sure exactly what you have in mind is the usual issue.
Everyone talks about this. There's no clear way.
Yeah, h equals 0.
Okay.
So that makes it sound like it's hard
right.
to define time.
Yeah. All right.
So you have to somehow define it relative to something else that's in the system. But now it becomes a sort of more approximate and sort of emergent notion.
I thought h psi equaled 0.
Well, yeah, so as an operator on the space,
that's
so physical
because
states,
H is
that means
0?
h equals 0.
It's also classically, by the way.
Yeah, it's a classical statement. I mean, it's true also quantum mechanically, but it's just classically true. I don't know.
And part of the reason we like ADS-CFT so much is we can kind of finesse that problem, because we do have dynamics on the boundary. But if we want to consider quantum gravity when there is no boundary, then we have to think about things differently and say something like, well, there's part of the system we can think of as a clock, and we talk about how it's entangled or correlated with other parts of the system. I also was going to give an answer for Scott, since he passed. And I think it's actually empowering for physicists to know more about complexity classes. I don't really know much about complexity classes. But I've gotten to the point where I'm not as intimidated as I once was when somebody says that something makes the polynomial hierarchy collapse to the third level. And some of that makes me feel better. But in the case of, Scott has this complexity zoo, and he can walk through the zoo, and he knows all the animals and their behavior.
I don't know them all. That's why I had to make it zoo.
He knows many of the animals, and he sort of has an intuitive understanding of their behavior and anatomy, which I lack. And I think we're recognizing complexity as an increasingly important concept. And in particular, Brian and others have done beautiful work relating complexity to geometry. And as complexity advances, that means geometrical changes occur, in particular behind the black hole horizon. So a deeper understanding of complexity is going to be part of the story of understanding what's inside a black hole. And of course, computer scientists should try, it's not easy, to understand more about holography. And we can't, I can't blame them for not understanding the holographic correspondence. I don't really understand it either. But I think part of what's starting to happen, and it was evident in Daniel's talk, is that some of the ideas can be abstracted or expressed in a form that, they are problems that computer scientists can think about when it becomes a question about an error-correcting code or about computational complexity. Then it becomes something computer science can sink her teeth into, and I think that's going to help to facilitate progress too.
Yeah, so following on the trend of cracking on my own field, so I think one thing that computer scientists should know about physicists, not physics, is that we're not good quantum computer scientists. We're not even good classical computer scientists. So this is something that's relevant not only in the application of computer science to quantum information theory or to the study of entanglement, but is actually relevant even to the study of other fields, other subfields of high energy physics. So here's an example. An example is the conformal bootstrap program, which some of you may have heard of just colloquially from colleagues at various places. In some sense, the conformal bootstrap program is nothing more than solving very, very specialized instances of semi-definite programming. So the people that do it right now are mostly physicists who may or may not have been trained as computer science, by and large not. So that means that they've written algorithms that solve this particular special instance of semi-definite programming, but by no means are these algorithms necessarily the most efficient algorithms, or even necessarily close to the most efficient algorithms. So what I encourage the computer scientists to do, and the thing that I really encourage them to think about, is that if you see a problem that physicists are doing, don't assume that they necessarily have a good reason for doing it the way that they're doing it. And like, if you have a chance to talk to them, to help them improve the way that they're doing things, generally they'll be very grateful after you get past the confused look on their face when you try to explain to them what an algorithm is.
Another approach which turned out to be very useful between physicists is a special method of proof, and proofs were actually mentioned here. This is known as proof by an EPR pair. I mean, you have a complicated problem and you map it to an EPR pair and you solve it. And many times it turns out to be fine. So that's how physicists usually sometimes prove. Anyway, one point that I was wondering about is this question whether one can use thinking about quantum information and general relativity, etc., and there are scales in between of condensed matter system, ultra-cold systems. Some of the ideas that people know in high energy physics, for example, the simply breaking pairs, Dirac pairs, name it. I mean, there are so many ideas. I think also Wilson was inspired by ideas from condensed matter or low temperature physics. They are related. They are the same. They have the same ingredient, the same mathematical structure, underlying mathematical structure. And the question is why. Of course, it could be that this is some idea that somehow physics at very different scales behaves very similar, like in the spirit of the normalization group. I'm not sure which it was actually asking it. Why is it physics so similar at very different scales? I'm not sure what's the answer, but maybe that's another kind of way to try to search for answers in other fields, like in quantum gravity.
Okay. I don't actually know to what extent computer scientists don't know this, but I think, in my experience, the concept of like a phase of matter and universality is something that is not widely appreciated in computer science. I think they certainly use this idea a lot, maybe without calling it that. But sort of the idea that you're robust to the details, that you have some large system that behaves in a way which is independent of the details, is an enormously profitable concept in condensed matter physics. And associated with that concept is the concept of renormalization and the flow of parameters. And so I think this is a, in physics we're kind of used to the idea that for different phases you may have to have different ways of thinking about the physics. And so I think, there could be some notion of different phases in computer science, or maybe that's complexity classes, I'm not really sure. But I think this is something for which there may be some profitable exchange.
Can I add something to that? Sorry for saying too, but it's really more or less the same as what he said. I just want to say it in a different way. I think another good thing that even condensed matter physicists have trouble with is the notion of the continuum limit. So working directly in the continuum limit is something which is extremely useful in quantum field theory. And I've often been to by sort of condensed matter minded computer scientists or even just condensed matter physicists where, they're saying something where if you think about it from the point of view of the continuum, it's sort of obvious, but it's being said in a very roundabout way, because everything is said in units of the lattice scale, and then somehow, I don't know. So of course, the downside to that, of course, is, as John was saying, we don't know what the continuum limit is, in some completely mathematically satisfactory way, but it seems to, have a lot of power and magic to it, which, I think is something that somehow hasn't really percolated beyond high energy physics yet.
Okay, so I could add something. So Brian, I think phase transitions, we do know what those are. They arise even in looking at random instances of NP-complete problems. Renormalization group, we have no idea. I would love to understand it someday. But I did think of one thing that actually I do wish physicists knew, which is one of the most. I sort of let myself be used as a CS consultant for physicists, right? One of the things that I get most often is, here's this system. Can you prove that it's hard? Or, can you prove that simulating this is hard or something? And I think it would help people to have a clearer understanding of just what kinds of hardness results one can hope for and what one can't hope for, in the present state of knowledge of computer science. So, for example, that we're almost never able to say anything about the hardness of individual instances, right? We only know how to talk about hardness in, the asymptotic regime, right, where something is going to infinity, right? And even there, the kinds of hardness we can show, we may be able to show you need to make a lot of queries to the input. Just like Andrew was saying in his talk this morning, right? Sometimes we know that there's a query complexity barrier because you can embed parity into your problem or something. But now if you want to go beyond that and say that, you need to apply an exponential number of gates, in order to produce some target state or apply some unitary transformation, then almost never are we able to prove that sort of statement unconditionally. Because if we were able to prove it, then, we could also prove, P is not equal to NP and things of that kind, right? Rather, the best that we can hope for in that case tends to be conditional results.
Okay, yeah, maybe I'll just make a comment, some maybe advice that I could give to both physicists and computer scientists, which is that you don't really have to choose. I mean, we're sort of in an area which, has we're sort of in the nice position of being able to sort of think about questions from both a computational perspective and think about physics and use ideas from physics and use ideas from computer science. And I think that's one of the, for me, one of the really fascinating things about quantum computing, that we can, see these two, disciplines coming together and, take insights from both and learn things about both. So maybe you don't have to feel pigeonholed. I prefer not to be.
All right, I think next we'll do a vote. And as we all know now, votes always result in good outcomes. So the question that we're going to be voting on is,
What is electoral college?
and the audience can join this too. So the question will be, what is the computational power of the universe? And more precisely phrased, what is the class of problems that can be solved with polynomial resources? And so it's going to be multiple choice. And so I'll write down the ballot. So we have so I'll have P. Here this is what classical computers do. And so this vote is in favor of quantum computers can't work even in principle.
Oh, or
and
they can be simulated like this.
Yes, or that they're equivalent to classical computers ultimately. And we'll do BQP. Here's, what? I'll say P equals BPP. Most computer scientists think that's the case, as I understand. So, what's that?
Maybe we should vote with that too.
Yeah. So BQP, here's quantum computers. And I think next we can put P space, thanks to Scott's talk. And we'll also put other. But one thing I will exclude from the ballot is the correct answer, which is I don't know. That's not allowed, even though that's the correct answer. All right, so we'll go through the vote. So who says P?
Before you call a vote, are we going to define what you mean by the universe? And specifically what I mean is, are we postulating an observer that lasts an indefinite length of time?
Right. In our actual universe?
Well,
This is a very important question.
so I mean, there's sort of an issue here, which is that these complexity classes are defined asymptotically, you know, in the limit where the problem size goes to infinity. And you could say, well, our universe, you know, maybe you can only access finite degrees of freedom, and so this, all of asymptotic complexity is irrelevant in some way. My inclination is to just say, well, you know, go to very large but finite n. Are these scalings going to look like polynomials or exponentials? Now it becomes like kind of a poorly, not an imperfectly defined question, but...
No, you answered my question. Yes.
Okay.
An observer that can pass an indefinite.
Yeah, okay.
Or one could say take the limit as the cosmological constant goes to 0.
Mike, let's say that they go into a 0 cc vacuum with exactly
That's the sort of thing. That's
Yeah,
right.
okay.
Is it possible to vote for the first one without actually having to also agree on the second one? Like, doesn't like if it's P, then I mean we know that BQP is inside the universe.
No, this is the largest
Yeah.
class.
We're saying...
No, but how can one vote for P but not vote for BQP?
Yeah, so the largest one.
The largest class of problems out of this list that can be solved with
P, but not more.
polynomial resources. So, you know,
P, but not more.
But how can
P is inside of BQP, which is inside of P space, and
If you vote for P, you're saying there is no problem which is not in P which can be solved.
yes, right. Well, I guess you're not voting for that one. All right, so all right, so how many people say P? Okay, 0. All right, who says BQP?
Come on, man.
Okay.
Who doesn't say BQP?
All right, well, we'll put that as the complement of the other sets. Okay, and who votes for P space or other? Okay, so other has 5. So my plan next was, for the person on the panel who had the most interesting vote, I would hand the microphone to them. But I guess everyone voted for BQP. Ah, okay, so you're the winner.
This is like the sort of thing you don't want to win. So the reason why I voted for other is because we just don't know what happens very close to a singularity, right? And we know that there are singularities that exist in de Sitter space. We know that there are black holes, and we know that we don't even know what happens, as has been said over and over again, inside the event horizon region of a black hole, even in the toy model of ADS. So in that case, when presented with the possibility of it works exactly the way that it works in low-scale physics, or it works in any other conceivable way, for me, I feel like the safer bet is that it works some other way.
I respond. Well, okay, so I guess what I would say is that, you know, of course I don't know the answer either, but, you know, near singularities, I'd be inclined to say, well, the curvature is very strong, and if you try to send your computer or your cell phone over there, it's not coming back.
I would say that in the whole history of physics, you know, there's been exactly one development which has changed sort of our conception of what can be computed in polynomial time. You know, when properly understood, right? And that was quantum mechanics, right? You know, relativity you might think would change it, but didn't general relativity? I don't think changes it. Quantum field theory, well, we still don't fully know, but the indications so far are that doesn't seem to change it. And so you know, so in all of physics, there's been one development, right? And so the way I think about it is that if there is another development, that sort of changes our conception of what's efficiently computable from BQP to something else, it will be something comparably enormous to quantum mechanics itself, right? Like a change to quantum mechanics. For example, if there were closed time-like curves, that would be enough to do the trick. You know, or more generally, if there were some nonlinearity in the Schrodinger equation, right? That would do it. You know, or some deeper theory to which quantum mechanics were only an approximation. But I think that is the scale of the thing that we're talking about here. You want to answer that? Okay.
I mean, I agree with everything you just said. I think that the key phrase that I took out of it, though, is when properly understood. And I think that when we're talking about quantum gravity and other things that are at those scales, it's not like quantum field theory where we physicists understand it but don't mathematically understand it. We don't even physically understand it. So it's entirely possible that once you get to that scale, something odd happens. And I think a sign of that is the fact that there is thus far no consistent answer to the information paradox.
Any other comments? All right, so we've kind of gone out into the far reaches of abstraction and, you know, very high energy physics. Maybe we can finish off with a question which is a little more down to earth. So this one is about what do people see as the most interesting and promising prospects for using quantum computers, especially near-term quantum computers, for helping us to solve problems in high-energy physics. This could be either analog or digital simulation, interpret it as you like. And maybe I'll just take volunteers for who wants to chime in first. You don't necessarily have to have everyone comment.
We're going to use quantum computers to get a deeper understanding of holography. And it might not be so long before that's possible. So it may be. So what's the essential thing in having a holographic correspondence? The string theorists would say you have to have strong coupling and you have to have large n. But the large n part means you have to have many degrees of freedom which all interact with one another. It's still a local Hamiltonian, but not constrained by geometric locality, and the strong coupling means very large quantum fluctuations. And we're going to have the technical ability to realize systems like that in experiments. And what we really don't know yet, because we don't have the analytic tools and we can't study it with digital simulations, is how generic is the property of having a gravitational dual? If you have a system which has many degrees of freedom interacting, and is it strongly coupled, does that give rise to something that it would be fair to call a gravitational dual description? I think that's something we're going to be able to probe eventually with experiments. How far off that is, I don't know, but part of the question is whether we can get interesting answers to questions like that without making use of fault tolerance, using relatively noisy nearer-term devices. But I think that's a really exciting way in which quantum computing may impact our understanding of physics.
So I said this briefly earlier, but I just want to reiterate that another avenue that's the hot topic in high-energy physics research right now that I think that quantum computers could be quite useful for, primarily as a computational tool, is the conformal bootstrap, to understand conformal field theories and their spectra in particular in better detail. Not only can I say that kind of in general, I can point to specific results in quantum algorithms that currently exist that could be relevant. So, for example, the quantum algorithm for semi-definite programming by Svore and Brandau could easily be something that pushes the conformal bootstrap method that relies on semi-definite programming to the next level. In much the way that if you followed the LIGO plots, the advance from LIGO to advanced LIGO or to LISA, they can indicate how far down their sensitivity increases from thing to thing. Once we have a general purpose or even a small quantum computer, one can probably anticipate a jump in the efficacy of the conformal bootstrap. Moreover, there's another method that seems relevant to the bootstrap, which is this algorithm by Harrow, Hassidim, and Lloyd for solving linear systems, where you don't necessarily obtain the solution of the linear system, but you can find out expectation values of matrix elements. This is also something that apparently is sufficient for the purposes of some aspects of the conformal bootstrap. So that's also an algorithm that exists, has an exponential time speedup attached to it. And as soon as a quantum algorithm is created, as soon as a quantum computer is created that has access to even a modest number of qubits, we should be able to dramatically outperform the best known classical algorithms.
Yeah, I would think it would be fantastic if those simulations of quantum lattice gauge theory would be able to somehow get the hang of dynamics, of real dynamics. I mean, imagine you can see the confinement mechanism in real time, where you can really look at the flux tube and measure directly the string tension between two quarks. I mean, this is something which is basically impossible in doing it in accelerators, because you just do some scattering experiments. Well, here you can measure things which in principle you cannot measure in other systems. So if it really simulates correctly the standard model, or even a small section of the standard model, which is not trivial, and it's two-dimensional rather than one-dimensional, it's enough that it's two-dimensional that you will see something which is really dramatic and fantastic. Hopefully, we'll come out with some also interesting physics and some at least new ideas how to do some new physics, but this would be fantastic to do something. But for this to happen, I think that one really has to go beyond one dimension. And what people can do now, which is also fantastic, is really have big lattices in one dimension. This is kind of getting very close, and simulate the Computational model. Maybe they will do something on a billion in one dimension, but this, maybe it's hard, but it's not quite like in two dimensions. And here I say that this is kind of still not here. I mean, maybe it's close, but I'm not sure. It's doing very fast progress, this direction called atoms. Also, other directions are kind of going forward, and maybe even more. So it surprises me that it goes faster than what I imagined. So maybe, hopefully, there is. I mean, in a period of 10 or maybe more years, we'll get some really non-trivial physics coming out of it. That's the goal.
Yeah, just comment on two things. So one which I'm not an expert in, but which I think definitely needs to be mentioned, is just in the context of condensed matter physics, for example, trying to nail down the phase diagram of the Hubbard model at strong coupling, right? I mean, what does that tell us about high TC? I mean, that's the kind of thing that clearly having a quantum computer with not crazy number of qubits would be helpful for. For things a bit closer to me, right? I mean, specifically in the context of the black hole interior, just in the last year there have been several interesting papers in ADS-CFT about the idea of using pulses of negative energy from the boundary to make wormholes traversable, which part of that involves the ability to evolve the system backwards in time. So it's the kind of thing that you can't do just in the lab if you don't have sort of complete quantum control of the system. But if you do, then it allows you to sort of extract information from really behind the horizon in the bulk theory and sort of just pull it out into sort of simple observables in the boundary. And previously we knew how to do it using sort of complicated observables in the boundary in roughly the same situations, but now it's really become a thing where sort of all you really need to be able to do is to run the system backwards. For the quantum computer does that for lunch. So I don't know, you can even imagine trying to see things about the singularity and so on. So I mean, maybe it's more or less what John said, but just maybe a little bit more of a concrete thing that one could try to do.
Daniel, if you can make traversable wormholes in the bulk, then can't you make a closed time-like curve?
So the wormholes are traversable, but not traversable. So you have to have an apparatus on both sides. So you can't send a signal. You can't send a signal through the wormhole faster than you could by just walking around the long way. Okay, so the interest of this is not that you can send signals through faster. The interest is that although you have to go around the long way as part of the algorithm, you directly see coming out things which, had you not done anything, would have been behind the horizon.
There was the Simpsons episode where Homer uses a wormhole to just like reach beers in the fridge while he sits on the couch. Sorry.
Quantum teleportation.
All right, thanks.
But it's quantum teleportation where you don't feel like you got teleported. You just kind of feel like you went through.
So can I just ask a question maybe about John's answer, or maybe anyone who has a better understanding than I do, which is probably everyone, about holography. So how concretely, would we, how concrete a proposal do we have now for sort of what we would do with a quantum computer to understand holography? I guess my sort of understanding is that, in the ADS-CFT correspondence, we have a good description of the theory on one side, but not such a great sort of description of the theory on the other side. Is there a concrete thing that we would simulate to sort of understand the nature of the duality, or is the sort of direction more exploratory?
I'm sure Brian doesn't.
Yeah, sure. There are many things. I think this backwards and forwards in time is pretty powerful and interesting. So, like, for example, you can use it to probe the bulk locality that Daniel was talking about. So to see that two complicated operators with a lot of overlap actually commute in some set of states, that would be quite interesting to see. First as a demonstration of the physics, and then to probe the limits of that as you turn on quantum effects, for example. I mean, you could probe the Bekenstein-Hawking formula and its quantum corrections.
But for that you won't need some dynamical description of gravity.
No, I mean,
You need the Hamiltonian in the CFT.
but you need the Hamiltonian. Or some operator built from the
So you
Hamiltonian.
do it only on the boundary, not on the boundary.
The
Well-
bulk Hamiltonian is 0.
By assumption, we have access to these sort of CFT-like degrees of freedom. I mean, we want to design an experiment that probes an interesting aspect of the bulk physics. So, so one example is bulk commutativity. Another example is black holes are fast scramblers. That means they mix information around rapidly. We don't know how fast ordinary things are at scrambling. That's another question you can probe, which is about the thing that John mentioned, about how generic sort of a weakly coupled gravity dual is. So yeah, there are concrete.
But this is again looking at the boundary or looking at the bulk, the things that you described.
Well, I'm manipulating boundary degrees of freedom, if you like. But
So everything is resting on the assumption that this is indeed a correct duality transformation described back home.
no, we would test that.
How?
I mean, the duality predicts that these two operators commute, and we would see if they commute.
Right.
Or the duality predicts that the system scrambles this fast, and we would test that.
You can say it John's way too. You can say the duality is a definition of the bulk theory, and now we can test to see if it has the properties we expect of the bulk theory. So then it's clear that you're just.
When you say test, what does that mean?
Well, you can measure. So remember, there's a map, that tells you, given an observable in the bulk, what's the observable in the boundary that it
So
corresponds to.
you did an experiment on the boundary.
On the boundary, yeah, the boundary. Because it's the physical versus the logical, right? So if you like, only the physical qubits are real. Okay.
Yes.
So now, of course, we could get into what is real. I mean, in some sense, I would say the logical qubits are real too. But in terms of in the lab poking at stuff, it's the physical qubits. So then all the operations are just performed on those. But then there are predictions for what will happen, which would be very surprising if you didn't happen to know that this is supposed to be dual to a semi-classical bulk.
Something that I'm missing here is that I thought this duality is well defined only if you have n equals 8 supersymmetry and some large number n of external fields, etc., etc.
But it depends how much you want. I mean, I give you an example with the three qubits.
This duality, is it obvious that it applies to situations which are not specifically tailored in this way?
You could study that system. I mean, you could
It's
say
definitely not obvious. It's definitely not
It's not
obvious.
obvious.
But it's a question.
My
It's a question.
No, my question is such an experiment going to allow you to test this duality in cases where you don't have supersymmetry and a large n number of fields?
Yeah, but why not just do that? I mean, why not do n equals 4 with n equals 15?
This is complicated. I mean, you need to have a supersymmetry and a lattice which you cannot have. because it's not
But you
global.
can. So people actually have done pretty well with n equals 4 supersymmetry on the lattice.
You're talking about
Unsal and Catterall.
simulations.
Well, yeah, they were doing classical. But one could. I'm not sure what the state of the art is for Hamiltonian. Yeah, I mean, I don't think it's like a priori intractable. I mean, we might start with simpler theories.
And then what is it that you're going to check to see if maybe it describes a black hole?
Well, Brian just gave a list of things.
Okay.
I mean, in some sense, I think it's actually more interesting to simulate the non-ideal ADS-CFT things, to study whether the predictions of ADS-CFT are universal.
Yes.
Right? Because otherwise you'll just probably get the results that you put in by hand. Another thing that maybe one can do is that currently one can just simulate what happens to a black hole, right? So if one approximates a black hole as a number of qubits, and then it Hawking radiates, which means every once in a while it kicks one of the qubits out and no longer interacts with it, and it continues to interact on the ones on the interior. This is a system that we can model now, but only for a very small number of qubits, because applying the random unitaries that govern the black hole evolution in the intervening time is very expensive for a classical computer. It's exactly what a quantum computer is designed to do. So if you're interested in looking at finite n effects of black holes and that sort of evolution to see whether that sort of a black hole is just a quantum mechanical system stupid model is correct, then that's something that you could very easily do with, again, a reasonable size one.
And in fact, suggestive development that indicates one might be able to do interesting things without unrealistic resources is the studies the last couple of years of what people call the SYK model for Saj-Devier and Kitaya. It's just a model of Majorana fermion modes with 4 fermion interactions without any geometric locality restrictions, and as originally formulated, it has disorder, but that is not necessarily essential. And it gives rise to a kind of gravitational dual description in a 1+1 dimensional space-time. So it's sort of the baby version of holography. And I think one lesson you can take away from that is that holography may be a more generic phenomenon than we learn about by studying in detail, large n, n=4 super Yang Mills, which is studied extensively because it has so much symmetry that you have greater analytic control over it. But to look for a broader universe of examples of theories that give rise to a holographic dual gravitational description, we may just have to do experiments.
All right, well, we have the room for a few more minutes, but I think we have a pretty exciting day tomorrow, so maybe we should call it quits. It seems like we've reached a natural stopping point. I've been pretty impressed with how everybody has not been falling asleep and for the most part not cracking open their laptops, although it probably helps that most of us are having trouble getting on the Wi-Fi. Any question?
I have a question for Harlow. So we heard a lot about, which was very interesting, on how quantum computers can help high-energy physics. I was wondering if any of you can comment on how the converse might happen, that these discussions that we're all hearing, how will it advance QRS and
Yeah, that's a great one.
sorry to barge into your panel.
Yeah, so I think that one of the main ways that physics can help computer science is as a conjecture factory, right? So in particular, there are many things that that physicists, when they're grappling to try to make their various computer simulations work, kind of empirically realize work that may or may not be well motivated based on known computer science principle. So when you have a situation like that, and then once they see that it works a few times, they'll extend it, they'll continue to use it without feeling the need to prove it. But computer scientists may find it interesting to prove these particular questions. Also, another thing that I've kind of observed is that computer scientists are often motivated by questions that are closer to pure computer science or to pure mathematics. Those are the frameworks that they feel most comfortable with. But oftentimes a problem that maybe is not a priori obvious from a computer science perspective will arise over the process of a physical simulation. And maybe these problems are interesting in defining non-trivial complexity classes, or maybe these problems are things that computer science can give algorithms to that are useful for other computer science problems that are not obvious from the beginning.
I mean, I can tell you that, I got involved in the sort of, it from qubit or quantum computing and quantum gravity type efforts, in the last 4 years or so, despite, basically being a complete ignoramus about, quantum gravity, right? But one of the main reasons I got involved was that the people who are, in this area, including Daniel, including Lenny Susskind, including Brian, including others, have just repeatedly been able to generate questions, that come out of ADS-CFT or out of thinking about firewalls, but which are just computer science questions that are interesting, even if you completely forget where they came from. Then it's a question, and then you have to think about it. It has its it's its own thing, right? I would love to if these ideas were also helpful in answering some of the questions, but. I've heard the speculation that, that maybe, ADS-CFT is literally an example of a quantum error correcting code. Maybe it could be a quantum error correcting code that's actually useful for something. Now, actually, I've heard that conjecture from some of the people here. I don't know if they still believe it or if they want to comment on it, but that would be one possibility.
Maybe it's true.
Maybe it's true. Okay.
It would be nice. It's probably good for something.
Yeah, maybe just amplify a little bit. The error correcting code is one example, and it's a very interesting example. But more generally, the suggestion of new data structures, new algorithms that come from high energy physics inspiration. For example, we heard a lot about from John, state preparation is a problem that he studied. And one way you could prepare a state is to imagine in an expanding universe, you start with something small and it gets big. So maybe you prepare the state of many qubits by kind of blowing them up in some, like an expanding balloon. And that's something you can actually use to prove theorems and to provide new preparation procedures that you can implement on a quantum computer. Another example is something where we may learn that something we thought might be hard classically is actually easy classically. So for example, in ADS-CFT, the way you describe thermalization is you put some energy in at the boundary, and there's no black hole to begin with, and that energy falls into the center and collapses to form a black hole. And that's the picture of thermalization. You start with something simple on the boundary, and it becomes something complicated at the end of the day. But the black hole itself has a very simple description in the gravity theory. Somehow all the complexity has been hidden behind the horizon. And so that suggests that maybe there's a way to describe dynamics, really from the CFT point of view, where that complexity is similarly hidden. Where somehow if you want to ask about only coarse observables, that you can actually have a simple description. And so that challenges us to think on the sort of many-body physics side, how we could design an algorithm that could perhaps follow the dynamics of a quantum many-body system for arbitrary time, provided you don't ask too many fine-grained questions. Right, so I think this is just maybe a sort of examples of what Scott was talking about, but where ideas from high-energy physics or questions or phenomena that occur really challenge us to think in new ways about many-body physics.
And just another historical example of where thinking like a physicist can lead to algorithmic insights. This was about 10 years ago, but Farhi and Goldstone, who are high-energy physicists, made a breakthrough in developing an algorithm which achieves quantum speed up for formula evaluation, and they did it by turning it into a scattering problem and using their knowledge of scattering theory. And actually, Andrew, in his work, has built on that insight using scattering gadgets for algorithmic purposes. And I think it's an example, and there are likely to be many more in the future, of a physicist's perspective on the problem gave rise to new algorithmic approaches.
Well, that was very successful. So are there any other questions from the audience?
So this question was mainly directed at Scott. I don't think I agree with this premise, but assuming that like near the horizon of a black hole, there's some other physics that probably changes what our notion of efficiently computable is to like something beyond BQP. Do you think the physicists could find first, or can computer scientists come up with this class themselves?
So I mean, one thing that I have tried to do, you know, as a hobby, is just try to think about, you know, if what was feasibly computable in nature were not BQP, then sort of what else could it plausibly be, right? Just forget completely about, you know, what we think is, what physical theories have actually been proposed, right? Just think about, you know, what other complexity classes are there in the vicinity, right? And that's actually kind of harder than it sounds, right? Like, because, what typically happens is that if you try to generalize BQP in any way whatsoever, you know, you can get something that's stronger, but it will be much, much, much stronger. Right, like typically, you know, if I add in anything like the ability to make post-selected measurements or the ability to apply nonlinear evolution, or I modify the Born rule so it's psi cubed instead of psi squared or something, then, you know, typically I will find that I then have the ability to solve NP-complete problems at the very least, and maybe even sharp P-complete problems. And, you know, if I do a little more, then I'll even get P-space, right, as in my talk. So I've been very interested in the question of, you know, what other physical theories, you know, could there be, even just as thought experiments, that would give you just a little bit more than BQP, right? And so, you know, I had one proposal for that in 2004 or so, which was, if you could see the entire trajectory of a hidden variable in a theory like Bohmian mechanics, okay, then it turns out that you would get the ability to solve graph isomorphism in polynomial time, and in fact to break any collision-resistant hash function in polynomial time. You could do Grover search in cube root of n time instead of square root of n time. Okay, so a little bit better, but probably you still couldn't solve NP-complete problems in polynomial time, you know, even there. Right, and there was more recently a paper by Adam Boland and others that, you know, gives a closely related model that has these same properties, right? But that's sort of the best that we've been able to come up with in the vicinity of BQP, right? And I would say that we haven't found anything that's nearly as natural, right? So, you know, like quantum mechanics, I like to say that, it's entirely possible there could have been some alternate history where mathematicians thought of it first, right? And only then did, you know, the physicists realize, but in fact that's not how it happened, right? In fact, this was sufficiently weird that you know, no one thought of it until experiment sort of forced it down everyone's throats, right? So given that history, right, if there is something else, you know, beyond, that's sort of like quantum mechanics, but not quantum mechanics, that maybe gives you a complexity class that's like, not quite BQP, but also not so absurdly beyond BQP that it's just, like science fiction and forget about it, right? Then, I hope that we could, figure out what that other thing was from pure thought. But maybe we would once again need experiment to force it down our throats. Yeah.
So of course, I agree with everything Scott said, but I think this is something also which physicists have known, for 80 years, that the battlefield is littered with the remains of theories that were supposed to be modifications of quantum mechanics. It's extremely difficult to modify quantum mechanics. And in fact, even there's a field which is supposed to be about, called Foundations of Quantum Mechanics, where they talk about modifications of quantum mechanics, but they don't have any. They just talk about, oh, say I had a modification of quantum mechanics that were like this, then what it would be like. And they have conferences that are like that, and there are never any modifications. So, I think there's a general rule here, which is that, if you just sort of try to random walk in theory space without any guidance from physics, it's usually not a good idea, right? I could make analogies to other fields in physics too, but maybe I won't. But, usually when we modify a theory that's been around for a long time and has done a great job, there's usually only two reasons why we do that. So one, like Scott said, is because there's an experiment that tells us that the theory is wrong and we don't have a choice. And the other option is because we find that theory is in tension or in conflict with another theory which we like just as much. And then we have to somehow figure out, and history is full of examples of both of these things, right? For example, Einstein inventing relativity by combining electricity and mechanics. If quantum mechanics is going to end up being modified, and I don't know whether it is or not, I will make a bet, which is that it will be modified because there is a conceptual problem which needs to be solved, and which quantum mechanics is not able to solve. I will bet with very high confidence that it will not be found by someone who just says, oh, quantum mechanics is kind of weird, let me see if I can think of something different.
All right, so I think nature being cleverer than we are and giving us mathematical structures that we couldn't have, or at least didn't come up with ourselves, is a very nice note to end on for this conference. In any case, our room reservation actually is running out now, so let's thank all of our speakers who have done a great job.